new vocabulary term we're going to focus on today, a tangent line, a tangent line. You guys hear tangent, you probably think of opposite over adjacent when we did SOHCAHTOA, all right? But in a circle, there's different lines that are called tangent lines. Everyone, and I know you could read the definition, but take a look at my diagram on the left versus my diagram on the right. All three of those lines on the diagram on the left are tangent lines. None of them on the right are tangent lines. Okay, so what makes a tangent line different from all the lines I have on the right? Hits the circle in exactly one spot and one spot only. Okay, then why isn't that a tangent? It hits the circle in exactly one spot, U. Why isn't this a tangent? It hits it at W, right? Everyone see the definition? A what? Line. If I kept extending this to make a line, it would hit how many times? Twice. If I extended this to make a line, it would also hit twice. All right, it's got to be a line that intersects the circle in exactly one and only one spot. If it hits it in two spots, that's a different name for a different day. Okay, but one spot only, and again, it's going to be on the outside of the circle, a tangent line. It's tangent to the circle. All right. Hurry up, let's go. I didn't really need this on a Monday in the second one. Let's go. What do you want? Any day now. Slide, which is always awesome. Fade. Clock. What else? Okay, here we go. There are your choices. Anybody for the cube? Fade. Slide. And you got to pick a direction because I'm not giving away that easy. So if you want, curtains. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it might be curtains. Clock. Star. Okay, curtains it is. Everyone ready? Promethean manor curtains. Promethean manor curtains. Everyone ready? Here we go. Promethean manor curtains. Okay, flip, I guess. Going backwards. Here we go. Okay, common tangents. All right, common tangents. Think of it as this. One tangent line, so it's got to intersect the circle how many spots? Once, but it hits each circle in exactly one spot. All right, so one line hitting each circle in one spot. Take a look at my, almost look like your old school Venn diagrams, a circle linked with another circle. I'm saying there's two common tangents. Let me show you what one is, and then you can find the other for me. Here's one common tangent. One line that intersects each circle in exactly two spots, or one spot, excuse me. Where's the other one then? Draw the other common tangent. One line intersects both circles in exactly one spot. All right, I'm assuming most of you are going down below here with a little bit of a horizontal line. Yep. Next one. They don't intersect at all, the circles. I'm claiming there's 4. Where are they? I'm claiming there's 4. Where are those 4? One line intersecting both circles in exactly one spot. Common tangent. Try to get 4 out. Try to get 4. Because I'm claiming there's 4. I got a lot of people right now have one on the bottom and one at the top. And we're trying to figure out where else I could draw the other 2. You could draw the other 2 right in between. Right here. One spot, and right here. So there are the 4. I'm not claiming anything for these 2 when they're just touching. How many are there? Draw them for me. How many do you think there are? Draw them. See a lot of people at least get 1 or 2 in here. How many are you claiming there are right now when they just touch? 25, how many are you claiming? I am saying 3 as well. 1, 2. A lot of people I saw. Where's the third one? Going through their point of intersection when they just touch. Yep, so 3 common tangents. And then what about this next one when now the circle's inside another circle and they're just touching? How many common tangents can you get out of that one? Prediction 28? 1 common tangent. Right where they intersect. There it is. Not done yet. I've shown you guys 1. I've shown you guys 2, 3, and 4. Is there a drawing you could do with 2 circles where there would be no common tangents possible? Could you draw a diagram right now where no common tangents are possible? All right, you may, I don't know, put it in the middle. None are possible because we've done 1, 2, 3, 4. What about none? Explain your diagram as best as possible for me here. 12. But they don't touch, correct. So here, there. Okay, I cannot get a line. Well, it intersects that circle, but what's the problem? Intersects the bigger one twice, and that's not a tangent line. So, all right. Everyone good? Common tangents. All right, here's the big theorem for today that's going to help you out. Well, got to go over. Can you guys draw me a circle, please, somewhere around this theorem? All right, draw me a circle somewhere around this theorem. Draw a tangent line, 1 tangent line to that circle. Okay, 1 and only 1 tangent line. Bless you. Mark the point where it intersects your circle. Mark the point where your tangent intersects the circle. I want to stop calling that the point where it intersects the circle now. All right, we have a name for it now, and these mathematicians are very, very clever. Watch the name of this. The point where it intersects the circle is called the point of tangency. Pretty clever, huh? I know. All right, it's called the point of tangency. That is where the tangent intersects your circle. What I'd like you to do now, guys, is draw a center of your circle and connect a radius from the center to the point of tangency. If that is given to you, a radius drawn to the point of tangency, you can read the theorem if you want, but if that is given to you, we have a radius drawn to the point of tangency, what do they look like to each other? They look perpendicular because they are. Okay, so if you draw a radius or a diameter, doesn't matter, to the point of tangency, it is perpendicular to the tangent. Every time will form a right angle. That's the big theorem for today. Draw any radii to the point of tangency, those 2 are perpendicular. Got the calcs ready? Let's apply this theorem now. Let's apply this bad boy. Any line, assume their tangent sees the center. Find the value of x. All right, so I have a tangent, and I'm drawing a radius to the tangent. 16, where's 16? 16? Here we go, stud. What's happening right around here at this angle if I'm drawing my radius to the point where it intersects, the point of tangency? Yep, so I got that. That's a right angle. Any thoughts on how to find x then? All right, got it. What do you got for me? All right. Okay. One application of how that theorem works. Everyone all right? All right, let's keep going. Other ways like, here we go again. Star. Clock. 1, 2, 3, 4, 5 clocks. Curtains. Go again. Slide, and you're going to have to pick it if it wins. 1, 2, 3, 4, 5, 6. Fades. 1, 2, 3, 4, 5 fades. Cube. 1, 2, 3. All right, let's make a decision. Sliding to the left. Okay, here we go. Slide to the left. So everyone ready? It's got to go that way. Your left. Okay, your left. I don't want to hear, well, what if I was going this way? All right, they're going this way. Or Promethean, man. Everybody ready? I hope it's curtains. Going this way. Here we go. Ooh, a little drop, huh? Okay. This is like, my blood is boiling right now. Like you have no idea. No idea. Star. Clock. 1 clock. Curtains. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 curtains. Slides. 1, 2. Fades. 1, 2, 3, 4, 5. Cubes. Okay, here we go. Curtains. Or Promethean man. Here we go. Curtains or Promethean man. Ooh, the old star. The old star. All right, going back. Here we go. Whew, 3 opportunities. 3 opportunities. Couldn't take it home. All right. AB is tangent to circle C. Different ways I can find x. Well, we know the radius drawn to the point of tangency is perpendicular. Now you have a right triangle where you know some information about the sides, so you can use Pythagorean theorem. Help me set up Pythagorean theorem now. Give me the value of both legs here. Value of both legs. Here you go, 7, value of both legs. Okay, x squared plus 8 squared. Everyone be careful here. Hypotenuse. How are you going to express the hypotenuse? 27? 2. Where's your hypotenuse up here? CA? That's more than 2. Okay, x plus 2 all squared. All right, so x squared plus 8 squared equals, all right, what are you guys doing here? Hopefully your algebra skills are tough enough here. You're just not doing x squared plus 4, I hope. I hope. Yikes. Yikes. Yeah, erase it. That's embarrassing. We're doing, hey, x plus 2 times x plus 2, yep. We're better than this. You do get x squared and 4, I agree, but you get a little something something in the middle, which I'm going to ask for somebody in a second. And what do you get in the middle there? X squared, 8, what do you get in the middle? 4x, up. Okay, when you start moving things over, what's going to happen to my x squareds? When I start moving things around, what's going to happen to these x squareds? They're going to cancel because I'm going to subtract 1 over and it's going to cancel the other one. So I'm just left with 64 equals 4x plus 4, and I'm hoping you guys can solve that from there. Solve for x, get it all by itself. And when you get to that point, x should equal 1. Nobody. 28? 15. All right. Questions? All right, number 3, name the right angle. Where is the right angle in that diagram? Name it. 7. CBA, yep. Radius to the point of tangency, right angle. Now here's a little something different. You're not given one of the legs, but you could still do Pythag. That's not an excuse not to do Pythag. Even though you're not given one of the legs, you can pretty easily find it if you know your circle facts. Here we go, 2, name a leg. X squared, and you know what the other leg, CB, would be? Well, that's, CA is the hypotenuse because it's across from the right angle. So, all right, I'll put 10 over here. But what about CB, the other leg? Oh, I do. Oh, I do. What's this bad boy acting as? So what's that mean about any other radii I draw in this diagram? Including CB. Everyone see that? CB's a radii. I know all the radii in this diagram are 3. And you guys can leave this in radical form because you're not going to be able to break it down. So just leave it square root of. Just leave it square root of 91. Let's not play around with the decimals. We don't have time here. And then where's my right angle on number 4 using the theorem? 21, where's my right angle? Yep. Okay, everyone hold off here for a second. Hold up. Because I know some of you now, well, actually, let me ask somebody. And I got a different suggestion. 10, what's one leg? Perfect. How about 3? $23. 9 because it's a radius. Thanks for picking up that in the last one. All right, so that's 9 squared. What about the other leg? 12 squared. All right, here's where I'm going to stop you guys. Because I know a lot of you would say the hypotenuse is x plus 9 squared. And you would do what we did over here, double distribute. You'd probably have to end up factoring here because the x squareds aren't going to cancel out. And I don't know how many people want to do that right now. I don't. So here's what my thought. Instead of doing that, why don't we just call the whole hypotenuse c squared? Because once you find the whole hypotenuse, what can I just do at the end of the problem to find x? Subtract 9 from it. And I think that's a little bit easier than doing x plus 9 times x plus 9, then trying to factor it at the end. So everyone all right on my plan? Just find the whole entire hypotenuse and subtract 9 from it. So you get 81, $1.44. What are we looking at here? 225. So what is the length of that entire hypotenuse? 20? 15? That's the hypotenuse length. So you guys told me to find x, subtract 9 from it. So that's going to be 6. All right, so just think about it before you start going crazy with the double distributing. I'm just already better doing this. Everybody, that was to the right. You left people, that was to the right. All right, little proof here. What I want you to do, I'm going to let you and your group take over. All right. I want you to label as many congruent parts as you can because take a look at what we're trying to eventually get. BA and BC to be congruent. And they're not congruent unless the BA and BC aren't going to be congruent unless the triangles are congruent. Even if you don't know the reason, just leave it blank and write the statement down. You and your group talk to each other for, I'll give you about 3, 4, maybe 5 minutes if you need it. All right, finding the congruent parts that make the triangles congruent. All right, get the triangles congruent if you can. I'll talk to you in a couple minutes. Talk to each other here. A lot of good things going on. Some of you are wondering, how do you get the triangles congruent because side-side angle is not a way? Good idea. Don't write that down on your paper. All right, one thing you know is true about that diagram. Definitely true about the diagram. 13. Okay, here you go. And I'm glad we brought this up right away. The theorem we have been working with today does not say right angles are formed, does it? Nowhere in the theorem does it say right angles are formed. What's it say in the theorem? That two lines are perpendicular. That's what goes into the statements. That theorem we're using today does not say a word about right angles being congruent. It says that the radius, in our case OA, is perpendicular to the tangent AB. And then we go on the other side of the diagram, we can say that OC perpendicular to BC. And here is the theorem written out in full. A radius drawn to, what do we call that point? Drawn to the point of tangency is perpendicular to the tangent. And I know it's a little wordy, but this theorem says nothing about right angles being created. All it says is that the two are perpendicular. Now, how do you get the right angles? That's an old school reason. It's a reason we've been using since October. So angle A and angle C are right angles, and that would be, what would be that reason that we've been using all the school year here? 26? There you go. If you said they were congruent, fine. I'm not going to say they're congruent because I know what reason is coming up sooner or later here. And you don't need congruent right angles to use this reason. So I'm just going to leave it the way it is. Other pieces that are congruent up here. Other pieces, 21. There you go. Get the old reliable. OB congruent to itself, reflexive. And there should be two other segments up here that are congruent. 19. AO congruent to OC because they're both what? Yep, and make sure we say what here? We're not going to say all radii are congruent because that's a false statement. All radii are not congruent. Maya? In the same circle, yes. All radii are congruent. All right, now you look at that diagram and you're thinking the right angles aren't in between, so you can't use side angle side. Side angle, you know I'm going to grill you and roast you if you ever write that down or say it. But they are right triangles. What's another method that we have in our bag? If I'm using two right triangles? HL. Take a look. Hypotenuse here is OB and the legs are the radii. So we can use HL. Anybody remember what I needed to write down before I was allowed to use HL? You needed to tell me they're what? Right triangles. Okay, you need to tell me they're right triangles before using HL. So triangle AOB and triangle BOC are right triangles. Anybody remember the reason why they're right triangles? Because they have right triangles have right angles. Now you can say they're congruent. HL, and then let it roll off your tongue why AB and BC are congruent. Those two segments are congruent because of a little thing we call 28. Okay, good. I always like doing a little proof here and there. All right, here's the good news. This is always going to be true that those two segments are congruent. Always true that those two segments are congruent. Always true. Based on a theorem, which you guys just proved, which is the following. Here's the theorem. How can you describe, somebody describe to me in a geometric vocabulary word what AB and BC are? Well, they are lines, little tangent lines, right? And they're both drawn to same point, B. So if I ever have that, everyone ready? Two tangents drawn to the same, I'm going to add a word in here, you tell me why. External point. What do I mean by external point? It's got to be outside the circle. So two tangents that are drawn to the same point on the outside of the circle are, what'd you just prove about them? Congruent, yep. And if you want to make a little quick diagram here, some people refer to this as the Partyhat Theorem. Anybody? The Partyhat? Good. Okay. All right. Just keep turning the page, all right? No more jokes, I guess. Here you go. A polygon circumscribes the circle. Hey, quickly, we went over this beginning of the circumscribes. That tells me where's the polygon? Outside the circle, which it is. So I'm going to try to find the perimeter of this triangle. Oh, boy. The only full side you guys know is 7, right? What about the other full sides? Here is the theorem you just proved. Ready? Take a look at this little piece right here. Does everyone see two tangents drawn to the same external point? We see that. Two tangents drawn to the same external point. So what is this little piece right here then? How long is this little piece? That's got to be 3 centimeters. Again, everyone seeing that theorem we just wrote down and proved. So now this side's 8. Can you guys help me with the other full side here? What's this little piece going to be? Two tangents drawn to the same external point. This piece will be 5. And what about this piece right up here? Two tangents drawn to the same point. This piece will be 4 for a total of 9. Perimeter of that triangle will be 24 centimeters. See what you can do on number 6 in your group, because I gave you 2 out of 3 sides. So 9 plus 8. How do you find the third missing side? Because the other side's not, hey, this is not 6 right here. These aren't two tangents drawn to the same point. They're drawn to 2 different points. So this is not 6. All right, get after it. Get after it. Just let me know how you and group approach that one. 15. How do I get to that missing part here?
You know, like the part of the one you don't know is 6.
Yep.
And so the 9 gets subtracted by 6, and that means that the lower part is 3.
Okay, so that's 6. Two tangents are on the same point. That's 3. Yep.
And then if you subtract 3 from 8, it's 5.
Okay, so these two are congruent. That means 8 minus 3 is 5. And what about these two here? They're congruent, so this ends up being 11. Got it. For a total perimeter of, what do we got, 28? Nice job. Anything from you guys? All right, let's try to review some theorems right now with 7 and 8. Try to find angle x. And 130 is referring to the central angle C. All right, 130 is referring to that central angle. How can I find angle x? You guys already learned today, if these are tangents and I draw a radii, what's being created right here in particular? This is a what right here in particular? A right angle. Is there another right angle in that diagram? Yeah, I have another tangent line and another radii drawn, so I have a right angle here. Does that help at all to find x? 12. How can I find x in this case? Because this is a four-sided figure, a quadrilateral. I know there's 360 degrees in every quadrilateral I work with, minus the two 90-degree angles and the 130 I was given. So x ends up being what, Frank? 50. There are no tangent lines in 8, so maybe you got to dig deep for some older circle facts. 50 is pointing to the angle. All right, so you can't use any tangent line facts here, but you can use a couple circle ones. Okay, how you approaching this one now? 15, what do we know here?
You know that one angle is 50.
Got it.
And both the radii are.
Okay, got it. Both radii are congruent. True.
Know that both the other angles are 50 as well.
In an isosceles triangle, angles across from the congruent sides are congruent. Got it. So x. Anything else before we end this on this tougher one here? All right. We got a tangent line, two circles, O and P. What's the value of x that connects these centers? Can you guys add in anything on that diagram for me that I did not already add in for you based on today's two theorems? Can you add anything on your own right now to that diagram which is not put in there on purpose? What could you add to this diagram based on the theorems we just went over? 15 again. What's zy?
25.
No, zy is a what?
Oh, it's tangent.
And what's oz?
Radii. Oh,
So,
right angle.
okay, here, and is there any other right angle?
Yeah.
Where?
For PY.
Okay. Everybody good? Hey, is that a rectangle up there? No, it's not, because I don't know these two, so don't tell me that's 25. Okay, that's not a rectangle. Can we make it into a rectangle, though? Can we split this quadrilateral up into a rectangle and maybe, say, a triangle? Here's what we're going to do, so I don't run out of time. Everyone see the shorter radii, 9. We are going to draw a horizontal line across that forms a rectangle and a triangle. So now we have a rectangle up top, and it doesn't really matter what your line looks like as long as you draw it across. If it's a rectangle, how long is this red line I just drew in? 25. Opposite sides are congruent. How about this distance right here from Z to where that line intersected the radii? That'll be 9. What about the rest of the piece here? 3. If this is a right angle, what's right next to it? If this is the right angle, what's right next to it? Another right angle. Does everyone see a right triangle up there? Everyone see a right triangle where you know 2 of the sides? And you can try to find the third side. Okay, so that's what you're going to do in this time, because you have another one tonight, I believe, on the homework. It's the last problem. Draw a line across from the shorter radii to the longer one, make a rectangle and a right triangle out of it, and do Pythagorean Theorem. Good job today.